We're going to conclude this lecture series with one last example, and we're going to be doing some machine learning today. And we want to do some plotting, so import matplotlib. And we're going to use, we'll need numpy, import as np, and we're going to use sklearn. And sklearn is just a toolkit for doing machine learning. And what's really cool about it is it comes with some data sets already, so you can really hit the ground running with not tiny little trivial data sets, but not huge and overwhelming and intimidating data sets. So the data set we're going to be looking at is called the MNIST data set. And before I do that, actually, data sets not load digits. A quick tour of sklearn. Scikit-learn is just this awesome tool or awesome machine learning package in Python, and you can do classification, regression, clustering, lots of cool model selection, and any of the basics you need to do. It takes care of a lot of the heavy lifting. Today we're going to be doing a classification problem, and I'm going to use support vector machines, which are a very useful tool. Actually, if we go to my website, I have a little write-up on them as well. Let's see here, support. Here we go. So the way I like to look at support vector machines is to it's a classification technique, and I like to just compare it to splitting data with a plane, or in this case, since we're in 2 dimensions, we're going to split it with a line, as you can see in this video, or in this image. And I mean, it's really just a nice, simple, like, dot product projection from one plane from one line onto another, and it's so useful. Yeah, if you guys want to go ahead and read this, I'll include this link. You can read about it, or you can read about it on the sklearn page. I'll go ahead and include the link there too. Lots of good examples, lots of good theory, and what's really cool, you can use more than just a plane, right? So if we use a linear kernel, we've got a nice little plane separating our data, but we can use the radial kernel or a polynomial kernel, and we get much better divisions along in the data. So again, it's a nice simple algorithm. It's fast, it's easy to explain, but it's incredibly powerful. So that's why I've chosen support vector machine, and I use sklearn just because it's such a really well-written package. It takes maybe half an hour to go from 0 to 60, and you're just good to go. You're ready to do machine learning with just a very simple interface. So anyways, let's go ahead and load up the digits data set. This is MNIST handwriting data set for those of you who are familiar with that particular data set, but we're going to use the sklearn version of it, and that's just a little bit nicer to load. And we're going to set our X data as the actual images and our Y data as the targets, target. And so we've got just a bunch of labeled images, and we need to know how many images we have, and then samples X, and I'm going to just get a random number random int. So I need this random number just to keep things a little interesting, really. Show X, and I want a pretty plot here. CMap dot interpolation equals nearest p dot title format. So we're going to quickly display one of the random images from this data set, and then we're going to show its label. So if we hit run, first run always takes a bit. And I'm going to add a code window. There we go. So there, we've got a digit that looks like a 0 and is labeled as a 0. If we run this now, it should hopefully run faster. There we go. Oop. There we go. And here's a digit labeled 3. Here's a digit labeled 2. digit label 5, right? Nice and simple. And what's important to remember is that these are images, sure, but they're actually numerical representations of an image. It's just a grayscale representation. So, we have a matrix. Each one of these numbers represents one of the little pixels. And so, in the white areas here, well, let's just label this guy right here. In the white areas, for example, in the top right, it's 0. At the darkest areas, the number gets good and high, up to 16. And so that's all we're looking at. We're looking at a two-dimensional matrix, and it's, I think, 8 by 8, right? So we just have 64 numbers. So the first thing we need to do is we actually need to flatten each sample so that instead of having a 2 by 2 matrix of 64 numbers, or excuse me, an 8 by 8 matrix of 64 numbers, we have a 1 by 64 matrix. So we'll just use NumPy again. It's so great how many convenience features there are in Python. This would have taken like 5-10 lines of code to write in other languages, and that's what I really love about Python. And then we're going to do something that's known as the train test split. Now there's a lot of ways to do this, but I'm just going to keep it nice and simple. And what we want to do with this, or the reason we do this, is we don't want to train on the same data set as we test on, because then we're just sort of, practicing for the test. We're teaching to the test. And we're actually going to teach our machine learning algorithm how to predict, given this list of numbers, this list of numbers is equivalent to a digit 3, and then if we go again, we can say this list of numbers is equivalent to a digit 8, a handwritten digit 8. But we don't want to just teach to the test, so we're going to split our data into training and testing samples. And samples 2, and then we have x test. In case you haven't figured this out, it's going to be xxx flat from and samples and beyond. Actually, I want 2 and beyond. There we go. I'm just going to get lazy here and copy paste. And our y-test is equal to that. And the classifier we're using, this is our classifier object, is equal to svm. We're going to use a support vector classifier. It's so simple. It's so great how simple it is to do all this stuff with sklearn. This is all we have to do. We instantiate the classifier, and now we just train it. Classifier.fit x train y train. And we go ahead and run it. This is just a little feedback to tell us how the training went, and we are actually ready to make predictions. And okay, so that's kind of boring because it's not giving us any feedback. Predicted. Let's just look at the first 10 predictions. Okay, so we're predicting 8559. That's kind of boring because we don't know what the input looks like. So if we add a new block here, we're going to images. The thing about machine learning, it's actually really easy, but there's a lot of tedious stuff around munging the data and making it look pretty and all that stuff. So that's what I'm doing now. X, and samples over 2. List zip. Predicted and y test. So we're going to take our input data and then we're going to zip it up along with the predictions and the actual value for that. And then we're going to pick another random number equals And then we're going to basically just do the same thing again with showing the image. Predicted rand IDX. And this time, since it's zipped up with 3 different things, we're going to show the first one. And we need to set the color map again. Actually, you know what? Let's leave the color map off. Interpolation equals nearest. Just because I want you guys to see what happens. And we need to give it a title. Digit guess. And we have the actual, that's 1 dot format. Predicted. There we go. So we're gonna we're gonna plot the image, and then we're going to label it with the guess and actual label, and we of course have to show it. And this is what happens when we aren't using a grayscale map. So this is the digit 1, and it does look like we got the guess right. This is obviously not pretty, so I am going to go ahead and make the CMap equal to cm.gray r. There we go. That's a little better. So we guessed it was 5, and looks like it was actually 1. And if we do it again, we guessed 2, and it's actually 2. Guess 5, it's actually 8. Okay. So we're getting, you know, not great, but decent accuracy on this. Digit guess 5, actual 0. And we can actually find the score of this. So classifier dot score x train y train. So it looks like it predicts perfectly on the training set, which is good. And then when we go to the test set, we get a score of 0.4. Okay, so that means, you know, the score ranges from 0 to 1, with 1 being the best. Actually, it can be arbitrarily bad. So if I do y train versus x test, must have a size error. That's fine. So it can get arbitrarily negative. That just means it's a really bad training. But what this means is our classifier object, our SVM classifier, is about 40% accurate on out of sample data. So it's not great, but we can start tweaking these, the input parameters for SVM. And if we so we have all these parameters we can look at for SVM, and we can tweak them and change things up. The kernel, you know, we can use a linear kernel or an RBF kernel or a polynomial kernel. You have to specify the degree. There's a C and a gamma, which are sort of the, you know, knobs on this algorithm that affect its accuracy. But the point is, we very quickly made a classifier that predicts things with, you know, not great, 40% accuracy, but it took us hardly any time at all to make this. You know, if we spent a day tweaking the parameters for this and running a proper train test split, we could easily predict this stuff. And what's really cool about sklearn, if we keep going backwards, actually we'll just do this, and